Okay, I said we'd be starting covalent compounds last time, and here we are with covalent compounds. Now, covalent compounds are more flexible. Nonmetals can form multiple bonds. Well, most nonmetals, the halides, the halogens, cannot. But a lot of nonmetals are capable of forming multiple bonds, and thus they can have multiple partners, and thus you can get fairly complex molecules. For example, a strand of DNA is a single molecule. But we are going to be focusing on what are called binary covalent compounds. That is, covalent compounds that only have two elements in them. But even with just two elements, as you can see, you can get a fairly broad array of different compounds. So you need to specify both which elements are involved. For example, in this case, nitrogen and oxygen. That's easy enough to do. You also need to specify how many of each element is present, and you do that using prefixes. So, as with the ionic compounds, it's element-tide. So you have nitrogen and oxygen, you can have nitrogen oxide, right? Well, yes and no. There's a nitrogen and an oxide, nitrogen oxide, nitrogen oxide, nitrogen oxide. Okay. Then you use prefixes to specify how many of each element there are. And these are the prefixes over on the right. Mono, di, tri, tetra, penta, hecta, hepta, octa, nona, and deca. That just gets you through the first 10. They get more complicated after that, and for the most part, you're not going to see anything bigger than that, just because for a binary covalent compound, it's not really possible to have too many of a single element. Okay, so there are basically, you just take these prefixes and you tack them on the front of the element's name. There are a few exceptions. Okay. So here we have nitrogen 2 oxygen, that's dinitrogen monoxide. No Roman numerals, just the prefixes, dinitrogen monoxide. Here we have sulfur with 6 fluorines, so that's sulfur hexafluoride. This is our first exception. Mono, you don't put mono if it's on the first element. Okay? So it's carbon dioxide, not monocarbon dioxide. Similarly, boron trifluoride, boron and 3 fluorines. Remember, boron is happy with 6 electrons, so that'll show up a lot, boron trifluoride. Now, another exception is that we tend to drop the final vowel if we're looking at oxygen. Okay. So, if you're looking at, say, into O4, then that is dinitrogen. The prefix for oxygen, or for 4, is tetra, and then you'd have oxide. But you drop the final vowel, so it's just tetroxide, not tetraoxide. Okay? You sort of an abbreviation. Okay. So into O5, take a second to think about what that should be. That's a long enough second. It's dinitrogen pent oxide. You still drop the A. Okay. The exception would be for di and tri. So CO2 is still carbon. Remember, no mono for the first element. Carbon dioxide. Okay. Or I guess ClO3 would be chlorine trioxide. Another place where you drop the vowel, mono. So CO is carbon monoxide. And you drop the O at the end of mono. So it's monoxide, not monooxide. All right. So that is how you name covalent compounds. and you don't really have any major exceptions except from the common names. Okay? And the common names are for things like water, H2O, ammonia, NH3, CHCl3 is chloroform, NO is not nitrogen monoxide but nitric oxide. Okay? You don't get the mono on either of those, and you change nitrogen to nitric. Some of these names, nitric oxide, nitrous oxide, this was before they came up with a standardized way of naming things, so you get some kind of weird behavior for that sort of thing. And a lot of things have common names, and they'll show up all the time. Some of these names are pretty much permanent, like water and ammonia. Others are sort of fading and may disappear entirely. We'll see. Another exception is the hydrogen compounds, but at least there's a system to the hydrogen compounds. This is something you might learn to hate. They are called different things when they are dissolved in water. Okay, so HF, when it's a solid, is just hydrogen fluoride. You dissolve it in water, it becomes hydrofluoric acid. HCl, hydrogen chloride, dissolve it in water, hydrochloric acid. HBr, hydrogen bromide, becomes hydrobromic acid. You're seeing the trend there, I hope. Hydroblankic acid. Okay, X is often used for the halogens. But this trend works for other elements as well. So HI becomes hydroiodic acid. But you can also get this guy right here, H2S. This is a toxic gas. It is the stench of rotten eggs. It's also bad for you. It's toxic. When it's a solid, it is rather straightforward hydrogen sulfide, not dihydrogen sulfide, just hydrogen sulfide. And then you dissolve it in water, and it becomes hydrosulfuric acid. And I want to point out that hydrosulfuric acid is different from sulfuric acid. Okay, hydrosulfuric acid is a weak acid. Sulfuric acid is a strong acid, and they're different compounds, different behaviors. Yeah, that's going to be kind of annoying, but you do what you do, right? This is one of those common name sorts of things that's never, ever, ever going to go away, because we use these acids all the time. But the hydroblankic acid thing is only when they're dissolved in water. Otherwise, you treat it sort of like an ionic compound. So hydrogen fluoride, hydrogen chloride, hydrogen sulfide, and so on. Okay. We can also look at non-binary covalent compounds. I personally won't be really covering those all that much. Because I don't really care for them. They're annoying. Maybe if you continue to take chemistry, that'll become important, and you will curse my name. But probably not. But organic compounds are a special class of covalent compounds that can become extended and do have their own naming convention. And since we have enough time, I'll go ahead and cover these. But only the most simple class of organic compounds, namely the alkanes. Okay? An alkane is the simplest kind of organic compound, and it is just the formula carbon NH2N minus 2. Okay? So if N is 1, then it's C2N minus 2. Wait, no, excuse me. It's 2N plus 2. That would have been terrible. You would definitely have cursed my name. So if N is 1, then 2 times 1 plus 2 is 4. That's CH4. If N is 2, then it's C2H6, C3H8, 4H10, C5H12. You might be seeing a pattern there. Okay, so these are all simple alkanes. Nothing fancy about them. Just carbons bound to as many hydrogens as they can, in a chain. Okay, so this right here is C3H8. Okay. Just as many carbons as you can fit around there. And that is, this guy right there. All right. And these organic compounds have their own system of naming, because why not? I blame the Germans. Germany was, it was before even before it was Germany, it was the center for a lot of chemistry study in the late 19th, early 20th century. So they made a lot of big discoveries. And when you discover something, you get to name it. And in this case, they named it with these prefixes. So prefixes 1, 2, 3, and 4 are different, but after that they end up the same: 5, 6, 7, 8, 9, 10. Pent, hex, hept, oct, non, and dec. Okay. And then because these are alkanes, they don't have anything else bound to them. They don't have any double bonds or anything like that. It just ends in ane. So for naming organic compounds, for this course, just for the first semester of chemistry, you only need to count the carbons. So 1 carbon is methane, 2 carbons ethane, 3 carbons propane, 4 is butane, pentane, hexane, heptane, octane, nonane, and decane. Okay. And that's all you need to know for organic compounds. So what do I expect from covalent compounds? You have to be able to go from name to formula, from formula to name. And because covalent compounds are so flexible, you cannot go from elements to name or formula. So just the two: name to formula, formula to name. And that will do it for covalent compounds and organic compounds. When we come back in our next lecture, we will start talking about polyatomic ions.